Hello students, I hope you all are doing good. So today we are going to discuss alternating current NCERT section 7.7 example 7.6 to 7.7. So this is the disclaimer. So after this lecture you will be able to understand voltage, current behavior and power relationships in AC circuits containing R, L, C components, including the practical significance of power factor cos phi in power transmission. And the next of topic that we are going to discuss today is example 7.6 NCERT section 7.7 power in AC circuit. So as we have discussed about the average power and instantaneous power in all the three circuits, pure resistive circuit, pure capacitive circuit and pure inductive circuit. Now we are going to calculate or derive the expression for power in AC circuit, means LCR circuit, and also we are going to see what is power factor and physical significance of power factor. And example 7.7. So let's begin with example 7.6. So there is a resistor of 200 ohm and a capacitor of 15 microfarad. Okay, so there are only two components. There is no inductor. So it is RC circuit. Okay, so we have discussed LCR circuit. This is RC circuit. You have to put the L equal to 0, or we can say XL equal to 0 in the expression of impedance or in the expression of current or voltage. Okay, then you don't have to alter the formulas. Okay, you just have to put the L or XL equal to 0 because there is no inductor. If capacitor is not there, then you have to put XC or C equal to 0. Okay, now a resistor of 200 ohm and a capacitor of 15 microfarad are connected in series to a 220 volt 50 hertz AC source. Okay, so what is this 220 volt? This is VRMS, RMS value of voltage. If it is not mentioned in the question that is it maximum value, it is RMS value or any other value, you have to, by default it is RMS value. And 50 hertz AC source, this is the frequency of AC source. So you have to calculate the current in the circuit. Okay, which current? It is not mentioned, so IRMS. Calculate the voltage RMS across the resistor and the capacitor. So you have to calculate the RMS voltage across the resistor and capacitor. Is the algebraic sum of these voltages are more than the source voltage? So firstly you have to calculate the RMS voltage across resistor and capacitor. Then you have to take the simple algebraic sum of both these voltages. So you have to compare it with the source voltage. So what is source voltage? 220 volt. So you have to compare it with the source voltage, or you have to see that it is more than the source voltage. If it is more than, if it is if it is more than the source voltage, then you have to resolve the paradox. So what is our mistake? If it is more than the source voltage, it should not be more than the source voltage, because we are taking power from source, we are taking voltage from source. How sum of voltages across resistor and capacitor can be more than the source voltage? Okay, so let's see. So what is given? R equal to 200 ohm and C equal to 15 microfarad. Okay, and VRMS equal to 220 volt. It is given, and nu equal to, frequency is given, 50 hertz. So given circuit is series combination. It is also given in the question that this circuit is series combination of resistor and capacitor only. There is no inductor. Okay, so results of series LCR circuit can be implemented by putting. So we can use the result for impedance directly by putting XL equal to 0 in the current and impedance equation. Only we have to put XL equal to 0. We don't have to alter the formulas. Okay, so IRMS equal to VRMS upon Z. How we can calculate the IRMS? It will be equal to VRMS upon Z. Okay, now IRMS is equal to VRMS upon, what is Z? Impedance. What is the formula for impedance? Root R square plus XC minus XL square according to NCERT equation 7.25a. Okay, now inductor is not there in the circuit. This is RC circuit. So you have to put XL equal to 0. So this IRMS will become R square plus XC square only. Okay, so this is again equation. Now put XL equal to 0. You will get IRMS equal to VRMS upon root R square plus XC square. Okay, now we know that what is R? 200 ohm. What is not given? X is not given in the question, but C is given. Capacitance is of 15 microfarad is given. Also frequency 50 hertz is given. So can we find omega from the frequency? And after finding the omega, we can find the XC, which is equal to 1 by omega C. C we know that 15 microfarad. Okay, so firstly we have to calculate the XC. So in order to calculate the current VRMS is already given. We need to calculate the impedance Z of the circuit. So to calculate the impedance, firstly we have to calculate the omega, which is equal to 2 pi nu. And after putting the value of nu, which is 50 hertz, omega will be equal to 2 pi into 50, which is equal to 100 pi radian per second. This is omega. Now omega is 100 pi radian per second. To calculate the XC, we will this capacitive reactance XC will be equal to 1 by omega C. Omega is 100 pi radian per second. C is 15 microfarad. So this expression is according to NCERT equation 7.17. So XC will be equal to 1 upon what is omega 100 pi, what is C 15 to 10 to the power minus 7, 15 microfarad. Micro is 10 to the power minus 6. Okay. So XC will be equal to 10 to the power 4 upon 3.14 into 15. Okay, so it will be equal to 212 ohm. Okay. So now calculating impedance. So XC will be equal to 212 ohm. Or and impedance Z is equal to R square plus XC square. Okay, so which is equal to R, we know that given in the question 200 ohm, and XC we have calculated 212 ohm. So put these values in the expression of impedance. So you will get Z equal to root 40,000 plus 44944 and Z equal to root 84944. So after taking root, Z will be equal to 291.5 ohm. Okay, so we have calculated the impedance. Now we will calculate the current. So what was the current? IRMS was equal to VRMS upon Z. Okay, so Z we have calculated 291.5 ohm and RMS value of current is equal to VRMS upon Z. So put the value of VRMS, which is 220 volt, and Z equal to 291.5. So IRMS will be equal to 0.755 ampere. Okay, so we have calculated the IRMS. Now second part, to calculate the voltage VRRMS. So this VRRMS means RMS value of voltage across resistor, and VCRMS is RMS value of voltage across capacitor. Okay, we can simply say it voltage across capacitor and voltage across resistor only. Okay, if we are not specifying anything, it is RMS value by default. If we are saying simply voltage and current, it is simply RMS value. Okay, so current is same throughout the circuit. So since they are connected in series, so current will be same, means IRMS value will be same throughout the circuit. Okay, as it is in series combination. So from NCERT equation 7.22 we have VRM equal to IMR, VLM equal to IMXL, and VCM equal to IMXC. We can write this expression in the term of RMS values only also. So if we put VRM, so what is VRMS? VRMS is equal to VRM upon root 2. This is maximum value of voltage across resistors. VRMS is VRMS value of voltage across resistance. Okay, so what is the relation between RMS value and maximum value? So VRM is equal to root 2 VRMS, or we can say VRMS is equal to VRM upon root 2. Okay, after putting VRM equal to root 2 VRMS and IM equal to root 2 IRMS. So root 2 and root 2 from both sides will get cancelled out. It will become a VRRMS equal to IRMSR. Similar for the other expression also. So we can write this expression in the terms of RMS value also. So they will be identical. Only maximum value will convert to RMS value. So voltage across resistor using equation 7.22, VR RMS is equal to IRMS R, which is equal to 0.755 into 200, which is equal to 151 volt. So voltage across capacitor using equation 7.22, VC RMS is equal to IRMS XC, which is equal to 0.755 into 212, which is equal to 160.3 volt. So we have calculated the VRRMS and VCRMS. Now we will take the algebraic sum of both these voltages. Okay. So VRRMS is equal to 151 volt and voltage across maximum voltage across capacitor. RMS value of voltage across capacitor is equal to 160.3 volt. Now after taking algebraic sum, it will come out to be VRRMS plus VCRMS is equal to 151 plus 160.3, which is equal to 311.3 volt, which is not equal to the RMS value of the source. It is more than the RMS value of source. What is the RMS value of source? That is 220 volt. What is the calculated value? We have calculated by taking simple algebraic sum. It came out to be 311.3, which is more than. Then how we can resolve the paradox? What mistake we are doing? So the sum 311.3 volt is greater than the source voltage, which was 220 volt. Is this possible? It is not possible because source is providing 220 volt. How voltage across the sum of voltage across both these components will be more than the source voltage? So actually while adding, what we are doing the mistake, we are not taking into account phase difference between voltage and current, or we can say between both these voltages. Okay, so actually by adding here above, we forgot to take into account the phase difference between voltage across resistor and capacitor. Okay, current is same in the series, IRMS. Okay, VRMS, the RMS value of voltage across the capacitor. So voltage across the capacitor will be in the phase with the current. Phase difference between the current and voltage across resistor will be 0. But phase difference between the current and voltage across the capacitor will be 90 degree, or we can say pi by 2. So there is a phase difference between voltage across capacitor and voltage across resistor. Okay, so we have not taken into account that phase difference. That's why answer is 311.3, which is more than source voltage. Okay, so we have to take into account the phase difference. So RMS value of voltage cannot be directly added. Only instantaneous values can be added directly. Okay, only instantaneous values can be added directly. RMS value and maximum values cannot be added directly. Okay, we have to take the phase. So how we can resolve the paradox? So this figure 7.11b from NCRT, if we remove this VL, because inductor is not there, so this VL will be 0, and also this VLM will be 0. Only VC will be there, VCM will be there, and VRM will be there. Okay, so VCM is like this, shown by this black arrow, dark black arrow, and VR is shown by this sky blue arrow. Okay, and phase difference between both this VRM and VCM, you can see phase difference is 90 degree. Okay, to find the resultant, we have to do the vector sum, because these phasors are actually vectors. Okay, to find the resultant voltage V, or we can say VRMS, we have to do the vector sum. So how we will do the vector sum? So voltages VR RMS and VC RMS are not in phase. Therefore, they cannot be added like ordinary numbers. So voltage phasor VR is in phase with the current. So this voltage VR is in phase with the current, and this VC lags behind current by 90 degree. Okay, current is in this phase like this along this VR. It is not shown in the diagram, but current is in phase with VR, or we can say VR is in phase with current, but this VC lags behind current by 90 degree. Therefore, source voltage VRMS will be the vector sum, not the algebraic sum. Okay, so what is the vector sum? So how we will take the resultant of the vectors? In the vector sum, how we will take the magnitude of vector resultant? How we will calculate the resultant of magnitude of the resultant, which is equal to a square plus b square plus 2ab cos theta root. Okay, now what is theta here? Phase difference between two vectors or two phasors, 90 degree. So cos 90 degree is 0. So that term 2ab cos theta can be eliminated because cos 90 degree is 0. Okay, only the square of both these phasors and root will be there. This is the vector sum. This is the magnitude, how we calculate the magnitude of resultant. So VRMS, this is the net voltage. Okay, resultant of these two voltages across the resistor and capacitance. This VRMS will be equal to root VR RMS square plus VC RMS square, which is equal to root 151 square plus 160.3 square. Okay, so VRMS is equal to root 22801 plus 25696, and which is equal to root 48497, and approximately equal to 220.2 volt. Okay, which is matching the value of, nearly matching the value of source voltage. Okay, this calculated voltage, calculated effective voltage in the circuit is matching the source voltage. So that was the mistake we were doing by not taking into account the phase difference. So this matches the source voltage. So paradox is resolved by considering the phase differences. So in circuit which are series combination of LCR or RC or LC or RL, any one of these circuits, it can be LCR, it should be LC, it can be RC, or it can be RL. So for all the circuit we have to take the phase difference also to calculate the effective voltage in the circuit. So phase difference must be taken into account in calculations. Okay, now come to our today's topic, that is 7.7 NCERT section, power in AC circuit, or we can say power factor. Okay, so firstly we will calculate the instantaneous power, then we will calculate the average power. So there is some calculation, complex calculation there, use of trigonometry is there. Okay, so you have to be strong in trigonometric identities. Okay, you have to remember some trigonometric identities also. So consider a series LCR circuit where voltage is V equal to Vm sin omega t. We saw that it derives a current in the circuit given by I equal to Im sin omega t plus phi. Okay, so in yesterday's class we have discussed about LCR circuits. Okay, so voltage source we have used same for all the circuits, V equal to Vm sin omega t. Okay, and current expression we have derived for the LCR circuit was I equal to Im sin omega t plus phi, and phi is the phase difference between voltage and current in the case of LCR circuit. Okay, so where Im is equal to Vm upon Z according to NCERT equation 7.25b. Okay, and tan phi was equal to Xc minus XL upon R, NCERT equation 7.27. Okay, so what is Xc? Capacitive reactance, XL is inductive reactance, R is resistance. So this is expression for tan phi. Okay, so instantaneous power supplied by the source will be, which is equal to Vi. Instantaneous, how we calculate instantaneous power? It is represented by small p, which is equal to Vi. So P equal to Vi. Put the value of V. V is Vm sin omega t and I is Im sin omega t plus phi. So let average power over a cycle be P. So average power will be represented by capital P. Okay, that is capital V will be equal to average of small p, and these angle brackets are representing average. So capital P average value will be average of this instantaneous value small p. Okay, so from expression of instantaneous power, so instantaneous power is Vi Vm sin omega t Im sin omega t plus phi. Now we are going to use the identity sin A plus B. Okay, so we are going to use the identity sin A plus B, sin A cos B cos A sin B. Okay, so here sin omega t plus phi. So omega t consider as A or phi will be considered as B. So sin A plus V will be sin omega t cos phi plus cos omega t sin phi. Okay, and this sin omega t will be multiplied by this expression. So P is equal to Vm Im, and this sin omega t, Vm and Im are constant, it will come out to of the bracket. So this is square bracket. Now this sin omega t is multiplied by the whole term, this whole term sin omega t cos phi plus cos omega t sin phi, this whole term, which came out from this expression sin omega t plus phi. We have used a trigonometry identity, it became sin omega t cos phi plus cos omega t sin phi, and this sin omega t is multiplied by the whole term. Okay, now sin omega t is multiplied by this term, it will become sin square omega t cos phi. Now sin omega t is multiplied by this term, it will become sin omega t cos omega t sin phi, and Vm Im are out of bracket. Okay, this is the expression. Now we are going to use another identity also for sin square omega t and for sin omega t cos omega t. Okay, what is that identity? So using identity cos 2x equal to 1 minus 2 sin square x. Okay, so this is the another identity. So if we are moving this, if 2 sin square x will be on the right side of the equation and cos 2x will come in the right side of the equation, so it will become 2 sin square x will equal to 1 minus cos 2x, and 2 will go there. So sin square omega t will become, according to this identity, 1 minus cos 2 omega t upon 2. And here in the second term, sin omega t cos omega t, if we multiply by 2 and divide it by 2, it will become 2 sin omega t cos omega t, which will result in sin 2 omega t upon 2. Okay, so after using these identities, this sin square omega t become 1 minus cos 2 omega t upon 2 multiplied by cos phi plus, and this term will become sin 2 omega t multiplied by sin phi upon 2. Okay, now this expression again, now we will take 2 common, 2 will come out. So Vm Im upon 2, it will become cos phi will multiplied in the bracket, so it will become cos phi minus cos phi sin 2 omega t, cos 2 omega t plus sin 2 omega t sin phi. Okay, again we are using one more trigonometric identity. Okay, what is that? So we will take this negative common, okay, so it will become cos phi sin cos 2 omega t minus sin 2 omega t sin phi. We will take this sin minus sin common from these two equations, from these two terms we will take this negative sign common, so it will become cos phi cos 2 omega t minus sin 2 omega t sin phi, and this is the expression for cos A plus B. So using identity cos A plus B, so by taking negative common, it will become cos phi cos 2 omega t, means cos A cos B, and minus sin 2 omega t sin phi, means sin A sin B. Okay, it will become cos A plus B. So P will be equal to Vm Im by 2 cos phi and minus sin that we have taken common, and this term remaining will become cos A plus B, means cos 2 omega t plus phi. This is NCERT question 7.29. Okay, where cos phi is constant and not a function of time. Calculation of average power in series LCR circuit. So P equal to Vm Im upon 2 cos phi minus cos 2 omega t plus phi, which is NCERT question 7.29. It is only the second term which is time dependent. So this cos phi is constant, it is not time dependent. So average of this cos phi will be cos phi. Okay, time dependent component is this second term. So this second term is time dependent, its average will be 0. Positive half cycle of cosine cancels the negative half cycle. Okay, so there are two halves, positive and negative. So over a complete cycle, its average value will be 0. So taking the average of this equation over one complete cycle gives the average power. So capital P will be average of this instantaneous power, which is average of this Vm Im upon 2 cos phi minus cos 2 omega t plus phi. Okay, P is equal to average of this P will be equal to Vm Im upon 2 cos phi plus 0. So average of this cos phi will be cos phi, and average of this cos 2 omega t plus phi will be 0. Okay, so final expression for this average power will be equal to Vm Im upon 2 cos phi. Okay, so we can write this 2 as root 2 into root 2. Okay, can we write? Yes. So we can write it as Vm upon root 2 Im upon root 2 cos phi. Now, what is this Vm upon root 2? What this quantity is? Vrms. What is this Im upon root 2? Irms. So final expression for power will be so P equal to Vm upon root 2 and Im upon root 2 cos phi. So it will become P equal to Vrms Irms cos phi. Mark it as 7.30 A equation. Okay. So quantity Vrms Irms is called as apparent power. So this, only this quantity Vrms Irms, it is apparent power. Okay, without cos phi, or we can say virtual power. Using Vrms equal to Irms Z. Okay, we can find other two forms of this power by using Vrms equal to Irms Z, or we can put Irms equal to Vrms upon Z. So it will become P equal to Vrms square upon Z cos phi, or if we are putting Vrms equal to Irms Z, it will become P equal to Irms square Z cos phi. This is equation 7.30b. P is the average power, so this P is average power along with this cos phi. Only this term Vrms Irms is apparent power, or we can say virtual power, but along with cos phi it is true power. It is called true power or real power. Quantity cos phi is called the power factor. Okay, so this cos phi, this factor which is used along the average power, is known as the power factor. Okay, so let's see the definition of this power factor cos phi. Okay, so what is this power factor? It is the cosine of phase difference between voltage and power. So phi is the phase difference between, so phi is phase difference between the voltage and current. Okay, so what is it is determining? It is determining the true power dissipated in the circuit. Okay, we know that virtual power is Vrms Irms. Okay, so this cos phi is representing the, so what is cos phi determining? According to phase difference. Okay, so phase difference will be different for different LCR circuits. So it is determining the true power dissipated in the circuit. Okay, not virtual power. So P is equal to Irms square Z cos phi according to NCERT equation 7.30b. So average power dissipated depend not only on voltage and current, but also on cosine of phase of angle. So average power not depends on only voltage and current according to the equation. It also depends on the cosine of phase angle phi between them in the LCR circuit. So now there are some special cases for this power factor. Okay, so case 1, resistive circuit. Okay, so in the case of resistive circuit, what is this phi? Phase difference between voltage and current in the case of resistive circuit is 0. Okay, so if the circuit contains only pure R, it is called resistive. In that case, phi is equal to 0, means cos phi is equal to 1. Okay, there is maximum power dissipation. So phi is 0 in the case of resistive circuit because voltage and current are in phase. That's why cos phi is 1, maximum value. Okay, so there is a maximum value of power. It is called maximum power dissipation when cos phi becomes 1. So power dissipated will be IRMS square Z. Okay, sorry, IRMS square R. So this is the maximum power dissipation. Purely inductive or capacitive circuit. In the case of purely inductive or capacitive circuit, if the circuit contains only inductor or capacitor, okay, in the case of inductor and both capacitor, phase angle between the voltage and current is pi by 2. Okay, in the case of capacitor, current leads the voltage by pi by 2. In the case of inductor, voltage leads the current by phase angle pi by 2. Okay, so in both cases, phase difference between voltage and current is pi by 2. Okay, so cos phi in case of minus pi by 2 and pi by 2. In the case of inductor, it is minus pi by 2. In the case of capacitor, it is plus pi by 2. Okay, for both values, minus pi by 2 or plus pi by 2, cos have 0 value for both these angles. Okay, so it means power factor in the case of inductor or capacitive circuit will be 0. That means the average power dissipated will be 0 even though a current is flowing in the circuit. Okay, even though current is flowing in the circuit, the average power dissipated will be 0. So that current is flowing but average power dissipated is 0. So that current that is flowing in the circuit, in this case, in the case of purely inductive or capacitive circuit, is known as wattless current because it is not producing any power, it is not dissipating any power. So this current is referred as wattless current. So what is wattless or wattful current? Let us see. So there is a IRMS current and VRMS is there, voltage is there, and phase difference between voltage and current is phi as represented in the diagram. Okay, so we will resolve IRMS, this phasor of this I current IRMS, we will resolve it in the terms of two components. So IRMS cos phi, which is along this voltage VRMS, and IRMS sin phi, which is perpendicular to this VRMS. Okay, so phase difference between IRMS sin phi and VRMS is pi by 2. So this current, due to this current, no power is dissipated in the circuit. So this IRMS sin phi is known as wattless current. Okay, so wattless current component of current IRMS sin phi, that is 90° out of phase with the voltage and does not contribute to the average power dissipation. So it is in pi by 2 phase difference with the voltage. That's why no power is being dissipated across the inductor or capacitor or in the circuit. So this component of current is known as wattless current. Got it? Okay, in the case of capacitor or inductor also, the phase difference between voltage and current is pi by 2. That's why power dissipation is 0 across capacitor and inductor, and this component is known as wattless current. Wattful current. What is wattful current? So component of current IRMS cos phi, which is in phase with voltage, which is along the voltage phasor. Okay, that component contribute to the average power dissipation, and this component is called wattful current. Okay, there are two components. If the current flowing through a circuit, or we can say if across any component voltage and current is having pi by 2 phase difference, then power dissipation will be 0 and current across this component is known as wattless current. Okay, if current across any component and voltage across any component are in phase, okay, and this current flowing through that component is contributing to the average power dissipation, we can say the current is wattful current. Okay, now case 3. In the case of LCR circuit, so in LCR circuit, power dissipated is given as IRMS square Z cos phi. Okay, so IRMS square R as cos phi equal to R by Z. So this IRMS square Z cos phi can be written as IRMS square R as cos phi equal to R by Z. How cos phi equal to R by Z? According to impedance diagram. We will see in the further slide also what is impedance diagram. It is shown by a right angle triangle, and base is resistance R, hypotenuse is Z, and perpendicular is XC minus XL. Okay, and there is an angle between hypotenuse and base, that is phi. So cos phi we can calculate it from here, base upon hypotenuse. Base is R, hypotenuse is Z. So cos phi is R by Z according to impedance diagram. So if we put cos phi in the expression P equal to IRMS square Z cos phi, then it will become IRMS square R. Okay, so even in this situation, even in the LCR circuit, power is dissipated only in the resistor, because across capacitor and across the inductor, power dissipation is 0. So even in this situation of LCR circuit, power is dissipated only across the resistor as P equal to IRMS square R. Now case 4, resonance. Okay, power dissipated at resonance in series LCR circuit. So what is power dissipated at resonance? So at resonant, XC minus XL equal to 0. We know that XC become equal to XL at resonance, or we can say XC minus XL equal to 0, due to which in the impedance diagram, perpendicular is XC minus XL. If it becomes 0, so hypotenuse and base is along same line, so phase difference becomes 0, and cos phi will be 1. Okay, in the case of resistance, in the case of resonance, phi becomes 0 because XC minus XL will become 0. So according to impedance diagram, phi becomes 0, cos phi becomes 1, and average power will be equal to P IRMS square R. Okay, so this is the maximum power dissipate. Got it? So in the case of resonance also, current becomes maximum. Okay, impedance becomes minimum, that is equal to R. That's why power dissipation is maximum in the case of resonance. Okay, and circuit will behave like a purely resistive circuit. That's why average power will become IRMS square R. So resonance case is similar to purely resistive circuit. Okay, also IRMS equal to VRMS upon Z. So at resonance, Z is minimum and current becomes maximum. That is, maximum power is dissipated in a circuit at resonance through R. Okay, so next question, next example 7.7. So A, for circuits used for transporting electrical power, a low power factor implies large power loss in transmission. Explain A part. In A part, you have to explain that for circuit transporting electric power, low power factor means cos phi. Power factor is cos phi. So lower value of cos phi implies large power loss in transmissions. Okay, so you have to explain this. Okay, so why low power factor implies larger power loss in transmission? And in B part, power factor can often be improved by the use of capacitor. How we can improve the power factor? By the use of capacitor of appropriate capacitance in the circuit. You have to explain this. Okay, so let's see the solution. So power loss in transmission line is given by IRMS square R, where IRMS is the current flowing through the line. Okay, so IRMS is the current flowing through the line, that is transmission line. R is the resistance of transmission line. So how power loss is affected? If we change the IRMS, if we change the resistance of the transmission lines. So we cannot change the resistance of the transmission line significantly, because length of transmission lines will be constant from one station to another station. length of transmission line cannot change. Okay, and thickness also cannot change significantly due to cost purposes. Okay, so resistance cannot be changed. So IRMS is the current flowing through the line. Now from formula of average power, P is equal to IRMS VRMS cos phi, where cos phi is the power factor. If we are decreasing the power factor cos phi, now to gain the same power, if we want same power B and we are decreasing the cos phi, we have to increase the IRMS. We cannot increase the VRMS. Source is same. If we are decreasing the power factor, we have to increase the current to gain the same power. If we are increasing the IRMS, so in the transmission lines, power loss is proportional to IRMS square. So power loss will be increased. So low power factor implies large power losses according to that. So since power loss in transmission line is proportional to square of IRMS square, so power loss will be more if we are increasing the current to gain the same power. Okay, for example, if we double the current, then power loss will become 4 times. Therefore, with the low power factor, the higher current needed to transmit the same real power. So we don't have to change the power. We have to gain the same power. If we are reducing the value of cos phi, we have to increase the value of I, due to which power loss will increase significantly. Okay, so transmit the same real power resulted in increase losses in the transmission lines. Okay. Now B part. Suppose in a circuit, current phasor I lags the voltage phasor V by a phase angle phi, like this shown in the diagram. So current phasor I lags the voltage phasor by V by angle phi. Okay. So this is the impedance diagram I was talking about. Okay. So how can we find the cos phi from here? So cos phi will be based upon hypotenuse. So cos phi will be R by Z. Okay, so power factor can be calculated by ratio of resistance and impedance. So now power factor using impedance diagram is given by cos phi equal to R upon Z. We can improve the power factor. How can we improve the power factor? Means power factor lies between 0 and 1. How can we improve the power factor? Means how can we make the value of power factor nearly 1? So if we are making the value of Z near to R, if we are changing the value of impedance and making it nearly equal to R, so cos phi will start tending to 1. If Z tends to R, then cos phi tends to 1. Simply. Okay, if we are changing the value of impedance and making it nearly equal to R, resistance, so cos phi will tends to 1. That means power factor will be tends to 1. So we can improve the power factor tending to 1 by making Z tends to R. How can we make Z tends to R? By reducing the difference between XC and XL. Okay, when this difference becomes 0, then Z will become to R. When XC become equal to XL, Z will become R at resonance. Okay, if we are decreasing the difference, then XC minus XL, this term will become smaller, due to which Z will tends to R. Okay. Let us understand with the help of phasor diagram how this can be achieved. Okay, so this is phasor diagram. Let us resolve I into two components. So we are resolving I into two components, IP along the applied voltage V and IQ perpendicular to the applied voltage. So this is IP, which is along the voltage, and IQ, which is perpendicular to this voltage. So this IQ is the wattless current, due to which no power is dissipated in the circuit. This IP is wattful current, due to which power is dissipated. So to improve the cos phi, to improve the power factor, what we have to do? We have to neutralize this wattless current. Okay, so current is there, but power due to this current is not there. Okay, it is wattless current. So we have to neutralize this to improve the power factor. So IQ is equal to Im sin phi. So this IQ is equal to Im sin phi that we have seen in the wattless and wattful current. Is called the wattless component since corresponding to this component of current there is no power loss. There is no power dissipation in the circuit due to this IQ. Okay, so it is called wattless component. IP is known as power component. This IP, which is along this voltage phasor, so it is known as wattful component, or we can say power component, because it is in phase with the voltage and corresponds to power dissipation in the circuit. Due to this IP, power is dissipated in the circuit. Okay, so it is clear from this analysis that if we want to improve the power factor, we must completely neutralize the lagging wattless current IQ. So we have to neutralize this wattless current because it is not contributing in the power dissipation. Okay, so to improve the power factor, or if we are improving the power factor, means we are improving the average power dissipation. Okay, so to improve the power factor or power dissipation, we have to neutralize this wattless component of the current. Okay, how can we neutralize this component? So it is clear from this analysis that if we want to improve the power factor, we must completely neutralize the lagging wattless current IQ. So we have to neutralize this IQ by equal leading wattless current IQ dash. So we have to neutralize this IQ with the help of this IQ dash, which is equal wattless current. So how this IQ dash will be produced? So this IQ dash is having pi by 2 phase difference with this voltage, and it is leading the voltage. So we have to introduce the capacitor. Okay. So how a capacitor helps? So they have asked in question that how power factor can be improved by the use of capacitor. So a capacitor creates a current that leads the voltage by pi by 2 angle. Okay. So this IQ dash, this component of current will be given by this capacitor. So in capacitor, the current will be leading this voltage V. Okay. So capacitor produces a leading current. So capacitor produces a leading component, IQ dash. Okay. This leading current cancels out the lagging current. So this leading current which is coming across capacitor will cancel out this lagging component. Okay, IQ. Only the useful current IP remains. Only IP remains because IQ dash will cancel this IQ. Okay, so only IP will remain, and this is useful, or we can say power component, due to which power is being dissipated. Okay, so let's see the summary. In AC circuit with R and C in series, voltages across components can't be simply added. We must consider phase differences between them and use vector addition. Okay, average power in series LCR circuit P equal to VRMS IRMS cos phi. Only the resistive components actually dissipates power. No power is dissipated across reactive, means inductive, capacitive components. Power factor cos phi shows how effectively power is being delivered in AC circuits. Power factor is equal to 1 for purely resistive circuits, and power factor is 0 for purely inductive and capacitive circuits. For mixed circuit like RC, RL and RLC, it is somewhere between 0 and 1. RLC means LCR circuit. We can write it as RLC or LCR anyway. Component of the current Im sin phi that is 90 degree out of phase with voltage is called wattless current. Wattless current does not contribute to the average power dissipation. Okay, we have discussed this. And wattful current contributes to the average power dissipation. In transmission lines, a low power factor implies larger power loss. Okay, there are some practice questions. 100 volt, this is RMS value. Okay, if it is not mentioned in the question, it is RMS value only. So AC source is connected to a series combination of R equal to 50 ohm and XL equal to 30 ohm. So what we have to calculate? The impedance, the current, the power factor, and the average power dissipated. Now second question, The RMS current in a circuit is 2 ampere and the impedance of 100 ohm. The power factor is 0.5. Then calculate the average power P. Third question, in an AC circuit, the power factor is 0.5. The apparent power, what is apparent power? VRMS into IRMS is given by 1000 volt ampere. Okay, calculate the true, or we can say real power in watts. So this volt ampere is watt only. Okay, we can represent power equal to VI. So volt ampere, it is known as watt also. Okay, so thank you, but we have to do the DPP. Okay, so this is first question. A wattless current exists in AC circuit when the circuit is purely resistive, the power factor is 0, the current is in phase with the voltage, the circuit contains only a capacitor and inductor. So what is correct option? You can write in the comment section. So what is wattless current? So due to wattless current, there is no average power loss in the circuit. So what is this condition? In which type of circuit? Purely resistive, when power factor is 0, current is in phase with voltage, or circuit contains only a capacitor and inductor. Yes, D. Everyone should write their answers. So in a LCR series AC circuit, the power factor is maximum. So when power factor is maximum, inductive reactance is greater than capacitive reactance. When capacitive reactance is greater than the inductive reactance, the circuit is purely inductive or circuit is at resonance. When power factor is maximum. Yes, D. To improve the power factor of AC circuit, a capacitor is connected in series. This helps because it increases the total impedance of the circuit. It provides a leading current to neutralize the lagging wattless component. It reduces the resistive component of the circuit. It decreases the voltage across the inductor. So we have discussed it in last example. So what is the correct option? Yes, B. In an AC circuit with a resistor, inductor and capacitor in series, the average power dissipated is I square XL. So for LCR circuit, what is the average power dissipation formula? I square R cos phi, I square XC or I square Z. This I is IRMS basically. Okay. At resonance in an LCR series circuit, which statement is correct? Impedance is minimum and current is maximum at resonance. Impedance is maximum, current is minimum, power factor is 0, or voltage leads by current by 90 degree. At resonance, what happens? What is impedance and what is current? Let's see. Okay, first option is also correct and this third option is also correct, but only one option can be corrected. Okay, thank you.